Okay, starting of part 2 of chapter 2. So we talked about the average velocity versus the instantaneous velocity. Average is just over an average of time, for example, over 5 seconds, over 10 seconds. But instantaneous velocity, on the other hand, is showing us on a very, very small period of time. Now, let's take a look at this. So we have a position time graph. It's a graph that shows the position as a function of time. Okay, or we call it xt. So every time that you see an xt graph, it means that this graph is providing you with information about time and position of the object. So for example, here, my object is located at this point, okay, at time t1, it is located at x1, okay? Then it starts to move, and it moves all the way to position 2. Now for position 2, when I looked at my watch, I looked and I saw that the time is t2. In this case, it's 4 seconds, for example. And I noticed that it is located at x2, just below 300 meters. Okay? If I draw a line, a straight line, from point 1, P1, to point 2, which is this green line right there, and I find the slope of that line. Okay, so I'll repeat it one more time. If you draw a straight line from P1 to P2 in xt graph, in position versus time graph, and you find the slope of this straight line, okay, then you have found the average velocity between these 2 points. Okay, so I can write down average velocity, which is a vector, is by formula delta x over delta t, and delta x is a vector as well, okay? And it is a slope of the line that connects them. Okay, slope of that line. Now, what is the slope of the line? You remember from basic math? The slope of a line, if you're looking at this, you have a angle here, which I would like to call it theta. Okay, the slope of the line is the tan of that angle. Okay, tangent of that angle is rise over run. The tangent is this area, this line, this amount, which is delta x over delta t. Rise over run. What is this? Oh yeah, we have seen it before. Where do we see it? Right here. It is V average. Okay, so every time that you have an xt graph, that means that you can find the average velocity if you connect the 2 points and you find the slope of the connector line. That's how you find the average velocity. Okay? For instantaneous velocity, on the other hand, you don't need 2 points. The 2 points are very, very, very close to one another. Remember the delta t goes to 0 for instantaneous velocity? So let's take a look at this. For example, position 1 is here, position 2 is there, okay? So if I want to, let me get rid of that for a second. So I want to find the position. So x1 here is 0, right? And t1 here is 0 as well at point 1. In point 2, right there on top, I have x2 being 2 meters and t2 being, oh no, x2 being 25. x2 being 25 meters, and t2 is 2 seconds, okay? Now, if I want to find the average velocity between these two, v average is delta x over delta t. Delta x over delta t, delta x is 25 minus 0, x2 minus x1. Delta t is t2, which is 2 seconds, minus t1, which is 0. And that means 25 divided by 2 is 12.5 meters per second. That's an average velocity between these 2 points. Now, if the delta t gets really, really small, meaning that my points are getting close to one another. If the delta t, if the time is getting smaller, if the time elapsed between these 2 points is getting very, very, very small, meaning that my points are getting very, very close to one another, okay? At some point, the 2 points are exactly at the same spot, meaning that if I find the slope of a line, then I'm just finding the instantaneous velocity. So in other words, the instantaneous velocity, which I just showed by v, I'm not putting a v average, is the limit of delta x over delta t, okay? But delta t is really, really small because these 2 points are getting close to one another. And what it means, it is the slope of tangent line. In other words, if you have xt graph, let me draw an xt graph. I have okay. I have xt graph here, okay, and this is the xt graph that I have. So what it does is showing you the position of the object at different times. For example, at this point, t1, the time is t1, and the object is located at x1. At this point, the time is t2, but the object is located at x2. If you want to find the average velocity between these two, you just draw a line between them, connect these two, and you find the slope of the line. The slope of the line between these 2 points will show you the average velocity. Okay. Now, what if I ask you, find the instantaneous velocity at this point? At this point, which has, for example, time equals t, and x equals x. Find the average find the instantaneous velocity at that point. Then what you do is you draw a tangent line. Let me see if I can draw a tangent line. So let's say that that's my line, the tangent line to that point, to the curve. It is connected to the curve. It is connected to this blue line. Only at one point it's tangent, okay? If I find the slope of this tangent line, then I have found the instantaneous velocity, okay? Not the average, because we are only dealing with 1 point. We're not dealing with 2 points. So, at any point of on an xt graph, the instantaneous x velocity is equal to the slope of a tangent to the curve at that point. And we just talked about it. So you know what I'm talking about. So for example, for this, if I want to find the average velocity, I have to do average velocity, v average, for this case, is rise over run, delta x over delta t, okay? You know the delta x is, it's given right there, 150. You know the delta t is 2 seconds, so 150 meters, not 20, 2 seconds. There we go. 2 seconds, okay? So the unit is meters per second. 150 divided by 2 is 75 meters per second, okay? For this one, average velocity, the average, and this is, by the way, a vector. Average velocity is delta x. What is delta x? 55 meters divided by delta t, 1 second. 55 divided by 1, that's just 55. So 55 meters per second. Okay. Now, if, see the time difference, the time elapsed time was 2 seconds here. Now it's 1 second, so the points are getting closer to one another. They were apart. Now they are getting closer to one another, okay? Now, if they get really, really close, I essentially have 1 point, this point, right? And the slope of a tangent line will show me the instantaneous velocity at that point. Okay, as you can see here, the instantaneous velocity then, or I'm just using v, I'm not using v average or whatever, I'm just using v because it's not average anymore. I have rise over run to find the slope or the tangent of this angle, okay? So I have tangent of theta, which is equal to a tan of theta, which is equal to rise over run, 160 meters over 4 seconds. And I have 40 meters per second as my instantaneous velocity. At that point, at that very point, right there, I was able to draw a line that is tangent to the curve, to the path, okay? And I found the slope, and the slope is showing me the velocity. How amazing is that? Okay. Here's another example. I have an xt graph, so just make sure that we're all in the same page, because if you see on a homework or an exam that there is an xt graph, it was like, oh, what is xt? No, it is position versus time. Xt graph. If you have an xt graph, And it looks like this red line going across. You want to find the slope. You want to find the average velocity between this point and this point. Okay, all you need to do is to find the slope of the connector line. And what is the connector line? Oh, it is exactly overplotted on the actual graph. So that's to our benefit, because now the slope is tangent of this angle. The slope is tangent of this angle, tan of theta. And tan of theta is rise over run, delta x over delta t, which is plus 8 meters. Oh, you know, we can get rid of the plus. We already knew it was a plus, right? So 8 meters divided by 2 seconds. So I have 4 meters per second as the slope. And we know what the slope is. What is the slope? Average velocity, exactly. Average V. Why is it average? Because we have 2 points. We have 2 points. Okay. Acceleration. Acceleration occurs when there is a change in velocity, okay? We actually feel it every day when we drive. If you drive, you know what I'm talking about. You sometimes drive with a constant speed, but you sometimes go up. Your speed goes up, it comes back down. You go up, you push and brake. You move, you change your speed, so you feel the acceleration. Okay, it is an increase in the speed, it is decrease in the speed, change of the direction of the speed, and it is defined as this. Okay, and remember, they are all vectors, so I have to have a vector on top of each one of them. So acceleration is delta v over delta t. Acceleration is change of the velocity, delta v, over the change of time. You know, the delta v is a vector. V is a vector. Velocity is a vector. It requires a magnitude and a direction. So delta v over delta t is acceleration, which is a, and delta v is v of final minus v initial. Delta t is t final minus t initial. Okay, and that is our formula for acceleration. Now, if you have a constant speed, if the problem is telling you that the velocity is constant, if velocity is a constant, that means it does not change at all. That means v final is exactly v initial. So when you subtract them, you'll end up having a 0 up here. And that means your acceleration is 0. So if velocity is constant, then acceleration is 0. And it is important, so I am going to put it in the box. Okay, average acceleration. Acceleration is a vector, as we said, so important. It has a magnitude and direction. We will normally deal with a straight line motion, so the acceleration will be in the same direction as the velocity or in the opposite direction of the velocity. Okay, the fundamental unit of acceleration are per second, or meters per second, or meters per second squared. Other units are, for example, kilometers per hour squared and things like that. We're not dealing with them. Boom. Don't worry about them. This is the units that we want to use for our problems. So acceleration, oh, is it possible that you have your velocity vector so is it possible that you have what did I do? I am trying to okay, I think it works now. So sometimes you gain a speed and sometimes you lose a speed, right? If you're gaining a speed, that means your speed is increasing by time, okay? That means you start, for example, from 5 meters per second, and by time, your speed is increasing. So 6 meters per second, and for example, 10 meters per second, so on and so forth, right? So you're gaining a speed, okay? That means the velocity and the acceleration are in the same direction. They're all in the same direction. They're either both positive or both negative. In other words, if you multiply them, you will always end up with a positive number. Positive times positive, positive. Negative times negative, positive. If you're gaining a speed, that means if you multiply a and v, acceleration and velocity, if you multiply them, you will end up with a positive number. However, if you're losing a speed, that means your speed is decreasing by time. If you multiply a and v, you'll end up with a negative number. So your velocity is positive, but your acceleration is negative. Your velocity is negative, your velocity is negative, but your acceleration is positive. Okay, so it's a very good practice to try to understand in your problem to see if you are gaining a speed in your problem or you're losing. Just simply by doing this, if they are going towards in the same direction, they're both positive, same direction, they're both negative, multiply them, positive, you're gaining a speed. Your speed is increasing by time. But if you multiply them and you end up with a negative number, that means you're losing your speed over time. Instantaneous acceleration. Instantaneous acceleration would have the same type of meaning compared to the instantaneous velocity. Now, remember the average velocity, average acceleration was delta v over delta t. Okay, we just talked about it. If you want to find the instantaneous acceleration, not average, because average is dealing with 2 points, 2 separate points, but instantaneous acceleration is only dealing with 1 point. Okay, so at that point, you have a limit when delta t goes to 0. Okay, or the derivative of v over t. Okay, the derivative of v over t means that if you take a derivative of v, you'll find acceleration. Okay, finding acceleration on a vt graph. Just like xt graph, you have a vt graph. So vt graph. Just like xt, we have a v. It's a graph that is showing you the velocity of the object versus time. So right here, for example, on point 1, position 1, I am having a time of t1. The velocity is v1x. At point 2, I have t2, and the velocity is v2x. Okay, if you want to find the acceleration, the average acceleration, a of average, is delta v over delta t, or a slope of the line that connects them. Okay, so if you're looking at this, I have an angle here. Let's call it theta. Okay, so the slope is tan of theta, and tan of theta is rise over run. Okay, rise is delta v, run is delta t, or v2 minus v1, t2 minus t1. And we already know what this guy is. We already know this guy is average acceleration. Okay, it's average acceleration. Now, however, if you want to find the instantaneous acceleration, for example, at point 1, rather than having a slope of a connector line, both of those points are at one point. So you have to have the tangent. So if I draw something like this, VT graph, and I have my graph like that, and I'm asking you to find the acceleration, instantaneous acceleration at that point, then what you have to do is to draw a tangent line and find the slope of that tangent line. Okay, the slope of tangent line at that point is your instantaneous acceleration. I am not putting a average here because it's not average. Now, the slope is tan of that angle. So tan of that angle is the slope, and the slope is instantaneous acceleration, or A. Okay, now this is the end of part 2 of the video of chapter 2. We will continue shortly with part 3.